Okay, my friends, this is going to get extremely interesting, for me at least. I I was always very, very scientific, and I still am. So how do you explain the existence of the universe and the existence of matter, existence of everything, the existence of intelligence, the existence of love and hate and art and all of these emotions and feelings and all of these things that exist? We know they exist. Where do they come from? This guy is a priest, and he came up with the Big Bang Theory. Now, this was in 1964, apparently. He was coming up with this Big Bang Theory. So now, he starts to state that everything started to come out from one single God source. Basically, that's the way scientists saw this and said, oh, no, that guy's crazy, he's a God guy, he's all about religion, he's a nonsense guy. And that's how they treated him originally. And then they see this cosmic background radiation. Now let me explain, let me let Anton Petrov, did I say this is his channel? Anton Petrov. Very good guy, but he totally missed this one. Now listen to this.
You might have guessed from the title or tone. As a matter of fact, the Big Bang Theory was barely accepted by anyone. And it's only a year after this was filmed, in 1965, that the scientists finally saw the evidence of the original prediction from his theory, the cosmic microwave background radiation, CMB, an undeniable evidence for his idea, and the definitive proof that he was completely right.
Alright, that's where we've got an issue. Let's try to understand what the cosmic background radiation is. They're talking about quantum foam at Fermilab, and it says empty space isn't empty. Okay, here's the deal. In the foam on the head of a root beer is complicated environment, bubbles appearing, disappearing, the dizzying display of change. Empty space experiences similar activity, subatomic particles, which I show you, winking in and out of existence. They're banging things and not banging things, hitting other things and not hitting other things, just sort of flowing through the not vacuum of space, because empty space is not empty. All right? These ephemeral subatomic particles are real, and they have a measurable impact on our universe. Absolutely. And what is the measurable impact? Light slows down. Empty space isn't empty. Empty space isn't empty. Light obviously bangs into those particles, so they flash off and then they turn down, they flash off, and that's what this bubbling, dizzying display of change is all about. This is Fermilab. They understand. And these are the particles they found, which are the same particles we found. And as they come out of the sun, they're coming out with dizzying speed, crashing into other particles, flicking on and off, just as they show here. That's what the universe is filled with. That's what the cosmic background radiation is. All right, let me just wrap the whole thing up, and then we'll look at bit by bit. These are the particles, the smallest particles that exist, which are these Dirac neutrinos. It's a black and a white ball. Fermilab has seen these same exact particles, and there they are right there, the black and there. And see, we have too, only we use light, so we can see them in exquisite detail. And this is the particles that are in space that Don Lincoln talks about. He calls it the quantum foam. I'm sure I've talked about it or will. All of these are from our light experiments. This is what particles of light look like. They see them sideways and they think they're waves and flapping this way. No, they're actually spinning particles. They spin this direction. They don't flap. All right, here's the spinning particles, and here's the way I can prove they spin right there. That's a spinning particle. Sometimes they go this way, sometimes they go that way. The slit is here, a single slit, no double slit, flip, flip, flip. It looks just like a drill bit. You can ask any machinist. Now, the particles are emitting from the sun. They're just in scads everywhere. They're everywhere in the universe. They're particles. They're particles of light. And I show them as particles of light, and you can see them in absolute no question whatsoever. They're particles of light. And here they are right here. These are the particles that are the light particles. And we can actually separate the black from the white in our Venturi. Right there. The black is separated from the white. That's fission and fusion. This is acceleration of the particle. The particle creates a wave, and here's what happens as light spins through the universe. It bangs all the other particles that are out there. That's why they twinkle and glow. They flash on and off. If they're not being banged, they don't do anything. If they're getting banged into, they twinkle. It's exactly what they say, and they understand this now, that the universe is not empty. It's saturated with these particles. It's obvious. Okay, there's red spinning like crazy going forward. Now, we can see that these particles are actually spinning in a circle. This is what happens here. Light spins. You can see it spinning in a circle. Now, as it hits the Venturi, some go over this way, some come under and go this way. So some go over the top and that way, some come under the bottom and go this way. So that way or that way. But most go through the center because it's being bombarded by particles all over the place. Light is not just one particle. It's just billions and zillions of them. So that's what's hitting this and spinning. So we can see light does spin going this way, but when they look at it as a wave sideways. You could look at it that way, and the longer the wave, the less the frequency. The tighter the wave, the more the frequency. Blue is tight as tight can be. Now, I think I have a shot here. Okay, here's blue. Look at that. Now that's coming through the Venturi, which is excited a little bit, and it's a little tighter than normal, but not much. When it comes out of here, it starts to open up, which is light slowing down. And it does this exact same thing in space. When it leaves the sun as, this is a solar eclipse. The moon is shielding us from seeing the brilliance of the sun, so we can see the particles. When they leave the sun, they are going as fast as they can possibly go. There's bits and pieces flying just incredibly fast, but you can see they're starting to slow down already. Obviously, they're going to slow down. By the time they hit the Earth, they concuss with our atmosphere out here. They're particles. They're particles. Just like Don Lincoln said at Fermilab, empty space is not empty. It's filled with this flicking on and off. And the only reason they're flicking on and off is because every now and then they'll hit a particle, and then they won't hit another particle again. And then they'll hit another particle, and they won't hit it again. Every time they hit one, they get slower and slower. And they end up being in that microwave range, which is almost like it's just everywhere. It's just everywhere. Because there's so much light that has just slowed down. It's really not doing anything. The only time it does anything is when it collides with something. Okay, I'm going to sort of finish it up right here. Light spins. There is no question about that. I've shown the spinning light. I've shown the spinning light. I've shown the spinning light somewhere else in here. All right. Now, light is made of these particles right here. Exactly like Fermilab says. These are the Fermilab particles, these are our particles, exactly the same. Only they see them in explosions of debris. We see them actually propagating and actually dividing. Here's where they divide. We accelerated that light. It turned into the particle we could see here. It's still a particle, you just can't see it. Then it turns into the particle you can actually see. Then it breaks here and separates the black from the white, and then refuses over here. So what we have just seen right here is this interaction right here. Where is it? Okay, right here. This is where it hits the Venturi, which is this tiniest slit will only allow the white through. And the white explodes when it goes through because it's forcing each field to crush in each other's field, just like they're hitting head-on, only the sideways. The black separates which is the muon neutrino, which is the black, separates from the electron neutrino. These two together make a Dirac neutrino. But when they concuss like this, they separate. The white goes into the shower, the black goes into a sterile muon mode. And this is the Dirac neutrino. Normally they're attached together, the black and the white. But when they hit, they separate, which is the holy grail of energy. It's called fission when they separate, and fusion when they come back together. And here it is right here. Fission is here, and fusion is here. So I don't see where I have to go much further with this. We're scrubbing through the galaxy on the arm of the Milky Way and ripping through whatever's in front of us. So the sun is colliding continuously with other particles, which forces it to scrub on this surface more pronounced. See the red spots? See the red spots? And you see the magnetic field around each red spot? That's because the sun is literally spinning like this, going that direction. Here's the poles, straight up and straight down. Here's the spinning scrub. So that is not only turning this way, but it's also going forward. So this is the real concussion zone. This is sort of just ripping backwards. So it's going this way, moving that direction. That's why we're seeing all of this debris. And that is debris. That is particles. There's some of them are just tiny little particles. They're the black ones, just the white ones. Sometimes there's black and white together. Sometimes there's 20 of them or 50 of them or chunks of them. Who knows how big they can be. But primarily it's very, very, very high charged particles. Once they get open in open space, they fill up that open space and they twinkle on and off as they bump into each other, but just for a second, just exactly as Fermilab says. It's a continuously twinkling mass in space. There is no empty space. The green is the same particle, and these are the neutrino values. As they begin to concuss, they change mass. And mass is nothing more than impact value. So here they have a certain impact value. Here they're getting a little more powerful. And that's what the neutrino flavors are all about. What else have I not shown you? I showed you acceleration. I showed you blue. I think I did slowing down. I showed you the green electron is identical, or the green photon is identical to the red photons. And here's the red photons right here. So this, as far as I'm concerned, this shows you that light is nothing more than particles. Particles fill space. Space is not empty. Particles that travel through a not empty space slow down. That's what the redshift is. It has nothing to do with the, well, we might be expanding. I can't say we're not expanding. The universe is not expanding. But I can tell you what, 100% certain, the universe, the particles are slowing down. That is no question whatsoever. And that is what leads to this very, very long frequency background radiation that they claim proves the universe is expanding. I say no. Show me some evidence that it proves it. It just shows me nothing. Absolutely nothing. Okay, if I could separate these two particles, what would happen? One of them has all mass and no glow to it to speak of. The other one is just the opposite. It's all glow and no mass. And that's what Don Lincoln from Fermilab says. Right down here it says, in summary, the extended particles have a fixed size. That's the black one. They may have a fuzzy edge around them. Point-like particles are mathematical abstractions with zero size. That's the red one. But even zero-size particles have an extended effect due to the effect of the field surrounding them. So it's strictly a field and no mass, basically, and that's strictly mass and no field, maybe a tiny little glowy edge related to the color that it's attached to, green, red, blue, as I show. Okay, these are the point-like particles right here, and that is the fixed particle, and it's exactly what we found. And we found that these can be separated, and we can actually see in an atomic bomb blast that they do exactly what Fermilab says. They carry all the weight, and this carries all the burn because of the effect of the field. Let's watch that happen. Now this is atom central, and this is an atomic bomb blast. The first thing you will see is the bomb will explode, and we'll see a big flash of white. And all that means is the white particles have gone first, because they're the outside. The black ones are the pushers. They push them, just like they push them through our Venturi. The black ones will push the white ones, and the house will explode. But the house does not explode until the black ones hit it, because the black ones have all the mass. Let's just bring it down to half power. Now, I'm going to open this up, atom central, here it goes. Atomic bomb blast. I'm going to shut the sound off. Boom. All it's doing is burning. Nothing moved. And then all of a sudden, here comes the black. Boom. That's it. Now watch. Everything comes back to its core. So let's look at that one more time. And I'm going to stop it as we go. The house is fine. Everything's fine. Now watch what happens when the initial hit of all of the white particles, which have no mass. Like Don Lincoln says, they're just nothing but fields. And they're but just their energy. They glow. Here it comes. The bomb goes off. Flash. Now watch. I just turn it off. I'm just going to click a couple of clicks through it. It's just sitting there fuming. All of the combustibles they're being so pushed against by these fields that they just, that's what they do. And that's what we did in our Venturi. That's basically what we had in our Venturi. Now that comes, boom. Well, we caused our particles to go around the black ones. And we did it with light. We didn't do it with atomic bombs, but we did basically the same thing. We did almost the same thing. You see this? We shot the particles down. They were all attached together here. And now we've got the white ones only hitting like the house, burning it. It's exactly the same thing. And then it came right back together here. So they separated here just like it did from the atomic bomb blast. The white ones took off ahead of the black ones. The white ones hit our Venturi, and they can come down like this and squirt through the Venturi. These can't. They go bam, 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 and they end up forcing and squirting and causing fission and fusion. All right, Tyson sent me this morning. This is from CBS News, and this is an event that just happened over the skies of Hawaii. Now watch this particle here. It's coming in this direction, and then it's going to have an event. I slowed this down to 25% of what it was. Now watch it come in. You see little streaks here and there. There's all kinds of little meteorites coming into our skies all the time. You see them everywhere, if you pay attention. Now, you see it starting to glow? Now, why is that happening? I am going to stop this every here and there. I'm not stopping it yet. You'll see when I do, and I will claim it. Okay, now watch now. It's starting to impact. And what is it impacting with? Our ionosphere. And what is the ionosphere? The ionosphere is the outer limit area of our particles. You say, what particles? I say, all the gases. The gases that are our atmosphere are traveling with our planet, spinning and being scrubbed through space. So anything that collides with that dense zone out here, if you want it to be, like calling it a firmament, that's fine too. It's like a shield around the planet that has our atmosphere, and it scrubs everything. So it's like you could call it a dome around the planet, around the globe. It completely encapsulates it, and as we spin and scrub through space, it collides with anything that's coming at it. Now, what is coming at us? I say everything there is consists of dipoles. So as it approaches the atmosphere, it's going to be pushed back at. That's why it glows, and it will impact these particles in the atmosphere. And there'll be a little glow around it in the front too, and then it will start to spin because it'll charge up and then it will spin. And that's exactly what happens. It's the exact same thing that happens as I can show you in our light experiments. Watch. It's continuing on, Look, bam! It hits our zone and pushes out a wave in front of it. It's exactly what happens in our light experiments. Now it starts to concuss further and further into this atmosphere. And then it will spin. It'll just start to spin. Because right now it's a polar molecule. So the glowy part is starting to get real glowy, and the dark spot, look at that. Look. I don't know if you can see that or not. I can see it. This is the dark spot. Let me home in on that real close, because I can see it. I don't know if you can or not. You see that dark spot behind it? There it is. That's amazing. Watch this. You know what? Let me bring it back a few seconds, because I saw it very clearly a few seconds ago. All right, so here it is. It's coming in concussing. It will get glowy in the front, and the dark spot will be in the back. Here it comes. All right, the black, watch it, the black. Keep your eye on it. It's a black. It's a little darker. I don't know if they call it black. There it is. All right, now look at how glowy that thing is getting now. And it's pushing all the particles in front of it. This is what happens in electron flood theory. Everything is a dipole. Out in front of it, these glowy particles are now pushing all the particles that are in our gases. That's what's this hue out in front. Now it will start to tumble, because don't forget, this is not coming straight in. This is glancing off the edge, and it will just start to tumble, and that's exactly what you'll see. All right, here it comes. It's coming in, it's coming in. You see, it's like two little glows. That's exactly what happens. This bottom part is hitting first, the top part is second. The bottom part is spinning, and the top part is spinning around as well. You see it? And now it's actually separating, and the glow is in the center. But this is the impact zone, this part here. And now it's trailing off, but it's still the forward impact zone is in the front. That's where the most impact is. Anytime you see the most glow, that's where the most impact is. And it's still glowing a little bit in the front, and there it goes. You see these things coming through? All right, that's about it right there. But you can still see it's still glowing in front as it impacts. That is the push to shove of particles. Okay, my friends, the devil is in the details. Now, whether the Earth is going this way, I'm not sure, or it's going with the incoming particle. However, this is concussing with this layer of atmosphere, which is around the planet. It completely surrounds the globe, a layer of really hot particles. It's thousands of degrees out there. It's not below zero. This particular area is thousands, because that's where it's scrubbing through the regions of space, which are saturated with particles as well. Watch that thing glow. Now keep your eye on this. The black particle now is starting to push the white ahead of it, because the black just goes. It's going to push. The white is saying, whoa, 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 there's all kind of stuff in front of me. The black says, I don't care. Just push ahead. Now watch this thing just explode. Watch. Watch it come forward. Watch this. Watch. This is very, boom. Watch it pop right up here. It's saying, I'm going to push you. And it's pushing hard against everything that's in front, and it's pushing back against its own black particles. And it'll go whoop, there'll be a pop right come out of it. Watch. You see it? See it vibrating on it? It's pushing, saying, come on, get out of the way, push. And it says, I know, boom. And then all of a sudden it says, all right, that's it. We're really going to get hot, buddy. And now it's getting hot, because it's trying to get through this layer of the atmosphere. All right, so that's what we end up with. This is this very serious glow in the front. And as it keeps moving forward, it starts to spin. All right, because it's going to spin. This is pushing here. You see it? Push, 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 and then it'll have this. Nothing else it can do but spin. And then it starts to spin, and that'll spin this way. And that has to also keep up with this spin almost. All right, now let's see what it looks like in the light experiments. We're going to see basically the same thing when two beams of light interact. This is virtually the identical same situation. The green laser is coming in here very, very high powered. You see how it's really interacting with the red, which is very weak. And it just pushes the red away. And the red literally spins. You see it spinning? That's the most unusual. That's the only time I've ever seen it is when the red is impacting with the green, and the green is just so powerful it pushes the red and forces it to spin around. And that's exactly what's happening. That particle was coming into our space and hitting against our layer and forcing it to roll. Simple as that.